All right, so we're finished with the first half of chapter 5 now. This is 5B now. In part 5A, we looked at sequences. Now we're going to turn our attention to series. So what is it that really separates a sequence from a series? As you can see here on this slide with a series, rather than having a string of numbers, what we have is a sum of numbers. That's the key difference. In other words, instead of taking A1, A2, A3, etc., what we're actually doing is adding them all up, and we end up with a single value. And so this now becomes a series. Most of the time, we'll be looking at infinite series. Now, this brings up a big problem. How do you add up an infinite string of numbers? Well, this is going to require us to use limits, as you can probably imagine. So the strategies that we'll use here will involve not just taking limits, but we're going to use a concept called a partial sum, where it sometimes makes sense for us to take an infinite series and break it up into finite portions. So for example, here, if you notice, I've got a partial sum where the terms only go all the way out to k. Okay, here they go all the way up to infinity, but here they actually stop at k, which is some finite number. And even if it's a large number, at least it's finite. And something like this, we actually can add up all the numbers. If we're pushed to the wall, we can do it manually just by adding them up. But usually there are very much more efficient ways of doing this. Now, here's a quick example. What if we have something like this? Now, this is an infinite series. And as you can see, there's a pattern here. 1,000, 500, 250, 125. And these are the terms that we will be adding together. Okay, so in other words, this by itself, what you're seeing here is actually a sequence, but we're going to create an infinite series out of these numbers, one term at a time. And the reason why we're doing this is because we're interested in the partial sums. So we're going to use the letter SK, S for sum, K for the index, to represent the sum of the first K terms. And we're going to call this the kth partial sum of the series. Okay, so let's take a look at the next slide and we'll see how this works. The first partial sum is just the first term, which is A1, of course. The second is A1 plus A2. The third is A1 plus A2 plus A3, which makes perfect sense. And then we have the fourth is A1 plus A2 plus A3 plus A4. And in principle, we will have an infinite number of partial sums, but it'll turn out that we can use these partial sums in many cases to obtain the sum of an infinite series. We're going to take advantage of any patterns that emerge. Now here, we're going to do something a little different. Here, what we're going to do is treat this as a series of terms where, let's say that these are dollars. Okay, for this is whatever we're referring to here, these are all measured in dollars. And of course, it's hard to see a pattern here. 1,000, 1,500, 1,750, 1,875, unless, here's a clever idea. Why don't we measure these terms in thousands of dollars instead of just dollars? Then all of a sudden, the pattern becomes a little bit clearer, because then what you've actually got here is 1 plus a half, 1 plus a half plus a quarter, 1 plus a half plus a quarter plus an eighth. Okay, so you go back here, you'll see that if you divide all these terms by 1,000, you'll have all of a sudden something that looks like a recognizable pattern: 1, a half, a quarter, an eighth, etc., etc. And so now it starts to become more clear. We can actually represent these partial sums with an actual algebraic formula. And what we're going to do is say that for any series, partial sum of a series, if we start at 1, then we can represent the entire series as 1 over 2 raised to the n minus 1 power. Okay, so let's demonstrate this. For example, when k equals 1, k equals 1, then S1 would therefore be 1/2, 1 minus 1, which is 1/2 to the 0 power, which is 1. When k equals 2, then S2 will equal 1/2 to the 1 minus 1 plus 1/2 to the 2 minus 1 power, which is 1 plus 1/2, etc., etc. Okay, all right, let's try one more. K3, 1/2 to the 1 minus 1 plus 1/2 to the 2 minus 1 plus 1/2 to the 3 minus 1. 1 plus 1/2 plus 1/4. So this is obviously correct. All right, so this is good that we've been able to reduce the partial sums into a formula. Now we can calculate any sum we want. And I think you can see where this is going. We can take a limit as k goes to infinity. Okay, in other words, here, this is a finite sum, but you know that the series goes out forever. So if we want to know what the sum converges to, we can do so by taking the limit. And in fact, if you look at the actual sums, so far we haven't actually added up these numbers. We have 1, 3/2, 7/4, 15/8. And if you were to continue doing this, you'd notice pretty quickly that these sums seem to be getting progressively closer to 2 without ever actually quite reaching 2. And by the way, one way you could do this, if you're really interested, you could just go into Excel and let's say put together your own terms without it taking all day. You could, for example, put n here, and then you would have 1/2 or just 0.5 raised to the n minus 1 power, and then you would have the sum. Actually, this oh, not yeah, that's right. Okay. So, for example, we have 0.5, and the exponent is n minus 1. So the first term is 1, then we have a half, then we have a quarter. And you can see these are getting very small. You've got a quarter, an eighth, a 16th, a 32nd, etc., etc. But the sum, the partial sums, first one is just the first sum. Then we have the sum of the first two. And so these are the ones that I was just showing you, except that they're in decimal form. We have 3/2, 7/4, 15/8. But if I were to continue dragging this down, watch what happens. Oh yeah, you can see they're getting really, really close to 2 without ever quite reaching it. So it appears that this series converges to 2. Okay, in other words, in the limit, this series has a sum of 2. Now, it turns out that with an infinite series, there's only 2 cases that we can encounter. Either it converges or it doesn't. Okay, if it converges to a finite constant. If it diverges, if it doesn't converge, then we say that it diverges. And that would be the case where, let's say, the terms are just continuously growing, or if they're alternating back and forth and there's no particular pattern. There's a lot of ways in which the series can be diverging. What we need for it to converge is that it's getting closer and closer to a specific constant like we saw here. And we can prove it with limits. Okay, so remember how we got started here. We took the actual series and we were able to express the partial sums as a specific formula. Okay, so like here, we've got n over n plus 1. And we want to know if this converges or not. Now, we see they're throwing us a hint here that we should probably think about using partial sums. Now, this one is a little involved. Let's do this. Let's just put together a table for this one. The pattern, the formula is n over n plus 1. And of course, here we'll have the sum. So here we'll have, for example, this number divided by 1 plus this number. And then we'll have 2 and 3, et cetera, et cetera. But what we're really interested in is this sum. So here we have the first term by itself. Here we have the second plus the first, et cetera, et cetera. So if you look at the pattern here, oh, whoops. G2. Let's see if there's any particular pattern here. Now, it appears just by looking at these numbers that they're just continuously growing. There doesn't seem to be any point at which the growth is slowing down like it did over here. Okay, you notice how it increased for a while and then it really started to flatten off or tail off. Here, that doesn't seem to be happening. So just looking at these numbers, it appears that this series diverges, that it does not have a limit that we can approach, at least not a constant. So if there is a limit, it's infinity. And that means that this series is said to diverge. Now, there's a formal proof of this, and it's a little bit involved. What they're basically saying is, look, if you can find a constant, like here, for example, what they're saying is look at these terms individually and compare them to a similar series that we might use where every single term is 1/2. Well, the reason why we're doing this is because then we can demonstrate, if you notice on the left-hand side, whatever we actually have is greater than simply adding up 1/2 to itself. And then here, 1/2 plus 2/3 plus 3/4 is greater than 1/2 plus 1/2 plus 1/2. So what this means then is that for any partial sum k, the actual partial sum is always greater than k times 1/2. So what that means then is that k grows, so does sk, and that never changes. That's basically what this is all about. We're proving that as k increases, so does sk. And so that tells us that the series is divergent. So this one is kind of an interesting proof. But here's an interesting one. Now, I think you'll like this one because, well, you'll see. It has some interesting aspects to it. 1 over n times n plus 1. All right, let's see. Let's do one of these tables again. This is the kind of thing that Excel is really good at. Lots of repeated calculations. So with I2 times 1 plus I2. And the sum, of course, starts out at 1/2. Then we add to that the next term. Now, oh, okay. Let me make sure that this worked out correctly. Yeah, I guess that's fine. Okay. No, but no, I knew something was wrong. No, the formula was not copied correctly. I knew there was something out of whack. If you look down here, you'll notice that these terms seem, the sums, I mean, seem to be getting progressively closer to one. And if we keep dragging this down, we can go as far as we want. And you'll see, wow, although it's taking its sweet time, yeah, it's getting really close to one. Some sequences, series rather, take longer than others to converge. So, but you can see it's pretty clear from these numbers that this one converges to one. But now let's prove it. Now, for this, we're going to use our old friend partial fractions. That's one of the reasons why I think you'll find this very interesting. Actually, no, we could have done partial fractions. It turns out it won't be necessary because here's why. You might recall that when you take a limit, let me just quickly, let's see. Whenever you run into cases where you have a limit of, let's say, infinity over infinity or 0 over 0 or something like that, there's often techniques we can use to simplify the problem and so that we can come up with the correct value. So imagine you have something like this. So direct substitution would give you infinity over infinity. So one of the techniques that you're allowed to use is this. Since you've got x squares in the numerator and the denominator, if you divide the numerator and the denominator by x squared, you'll have 1 plus 1 over x squared divided by 1 plus 1 over x. And you know that the limit as x goes to infinity of 1 over x to any power is just 0 because the denominator is getting very small. So that means this time direct substitution will leave us with 1. Okay, so we went from infinity over infinity to 1 because that is the correct answer. So that's exactly what's going to happen here. Okay, so in other words, this series, which you can see 1/2, 2/3, 3/4, it's pretty clear that these are converging to 1. The partial sum takes the form, if you notice, we have n, or in this case, k, over k plus 1. In other words, if you notice, the numerator is always the index k. And the denominator is just 1 more than that, 2/3, 3/4. And that will continue as long as we go out, all the way out to infinity. So the partial sum has its own formula. And so if we were to take the limit as k goes to infinity, direct substitution would give us infinity over infinity. We don't want that. So our clever strategy is to divide the numerator and the denominator by k. And so we end up with 1 over 1 plus 1 over k. And the limit of that is 1 over 1 plus 0. And we end up with 1. And that's what we would expect based on this result. You can see that the partial sums are getting closer and closer to 1 rather. And so that means that the series converges to 1. All right, now here's a special type of series that sometimes comes in very handy. We have something called a harmonic series. And so all it is the sum of 1 over n, 1 over 1 plus 1/2 plus 1/3 plus 1/4. I think these are useful in like different types of engineering. Now, it turns out this one is divergent, although it may not be immediately obvious. Why don't we use our special technique here in Excel to prove this? Now, by the way, this Excel stuff, this is not proving anything. This is just helping us see the patterns, okay? When you take the limit, then you are demonstrating that, yes, the series either converges or diverges, okay? It's 1 over n over 2. Okay, and then the sums. All right, now let's look at this thing and see if there's a pattern. See, now here's the thing. You look at these numbers and you notice what's happening is that they're just continuously getting bigger. Now over here, they're getting bigger too, but the differences between the numbers are getting smaller. In fact, you know what, maybe what we can do here is see if there's a pattern to the differences between consecutive terms. That might make it more obvious. What we're looking for in this column is that these differences are getting closer to 0, which is another sign that, yeah, this series is converging. And you can see that's what's happening. But over here, if I were to calculate the differences between the consecutive terms, I think you'll realize that that's not happening. All right, let's try that. So, yeah, you see what I mean? The numbers are, maybe they are getting smaller. Oh boy, it does look, all right, well, it does look like they are getting smaller. That's interesting. Let's get these out of here. I just want to see something. What happens if I keep dragging this down? I don't know. It looks to me like they're getting smaller, but very, very slowly. Yeah. Well, they're using that same technique from before, except with quarters. And oh, this is the proof. I don't know. This is very strange how it seems to be getting smaller. Unless I've done something wrong. I think the problem here is not so much that the differences are getting smaller, but in spite of that, the numbers themselves, you see, that's really, I guess, what the holdup is. Even though these differences are getting smaller, the actual sums are not, they're not giving any indication that they're getting closer and closer to a specific value. And I think that's why, like here, it's pretty clear that they're getting close to 1. But here, not so much. There's just, it's all that's really happening is that the increases are shrinking, but they don't show any sign of converging to a specific value. So this 0 test maybe isn't, sorry, this differences test maybe isn't the best idea in the world. I don't know. I thought it might be a good idea. I guess maybe not. But anyway, what you can see by this same technique we had before, it should be clear that SK is greater than 1 over K times 1/2, which means that there is no upper limit to how far the sum can go. All right, now we're going to briefly look at some algebraic properties only for a convergent series, by the way. These only apply when the series are convergent. So the first one is pretty straightforward. The sum of 2 convergent series could be reproduced by simply adding the 2 individually. We'll get the same results. Same thing is true with the differences. And then here, as you can probably imagine, the series CAN, we can just factor out the C and we'll end up with the same result. All right, now what that means is that we can take on some much more complicated series and determine if they're convergent or not. So like, here's an example, which at first glance looks like a nightmare, but in reality, we can rearrange it algebraically to give us what we're looking for. God, look at this thing. What are we supposed to do now? Well, actually, we've already had some experience with similar series. What exactly? Well, first we're going to break this up into a sum of two separate series. Then we're going to factor out the 3 here, as you can see. But now what? Now here we have to watch it because, and this is easy to overlook. This is actually n minus 2. We previously had n minus 1. This is n minus 2. So remember, let's go back here and revisit the first case we were looking at. This one. Remember this one, n equals 1 to k, 1/2 to the n minus 1, brought us to 2. Okay, so this one isn't quite what we need. So if we, let's see, algebraically, if I take this and divide by 1/2 to the first power, or just 1/2, that means that I actually have 1/2 to the n minus 1 minus 1, which is 1/2 n minus 2. So dividing by half, of course, is the same thing as multiplying by 2. So that's why this is here. Okay, that's the logic behind this statement. And of course, since we know that this one is 1/2, oh, sorry, 2, that means that this one, this new one with n minus 2 and then for the exponent must be 4. This one we just got through proving a little while ago was equal to 1. Okay, so that means that we're actually already done, because we know this series adds up to 1. And this one is 2 times 2. And the 3 is on the outside here, so we get 3 times 1 plus 2 times 2, which is 7. So because we already have worked with some of these other terms before, or these series, we can algebraically take this catastrophe and turn it into something much more manageable. And that's how this is done. Or it can be done. I mean, so in other words, when you run into these cases, the first thing you might want to do is think, does it remind me of something I've already seen, like 1 over n times n plus 1? If not, you can work on it separately and determine, using the techniques we had earlier, what it converges to, if anything. If it turns out that either of these two terms diverges, then the entire expression diverges. But here it converges to 7. And if you felt so inclined, you don't believe it, you can go back to our friend Excel, although you don't have to do this, but you might think about it. This is okay. I'm not even going to put this in the header. And here's the sum. So the n's go from 1 to 2 to 3, et cetera, et cetera. So here we're going to have 1 over a2 times a2 plus 1 plus 1/2 raised to the n minus 2 power. And then I'll do the sums. And so what we would expect to see is if I drag this down far enough, on the far right, the sum should get really, really close to 7. If I've set it up correctly. Oh, you know what I did? I just realized I left out the 3. Ah, Jesus, no wonder it didn't work. All right, that's more like it. And sure enough, yeah, you can see the pattern. It is getting very, very close to 7. It could take a while before we get there, but we're definitely getting closer and closer to 7. Okay, now, way, 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 way back in the beginning here, we mentioned that there's an arithmetic sequence and there's a geometric sequence. The arithmetic sequence is the one where the terms are separated by a constant difference. In other words, you have to, like 3, 6, 9, 12, that kind of thing is an arithmetic sequence. And a geometric sequence means they're being multiplied by the same constant, like 2, 4, 8, 16, 32. So it stands to reason that a geometric series is composed of a sum of terms from a geometric sequence. Okay. So in other words, this is what it looks like. Now, by the way, one of the things we'll be able to do with these series is take a very complex function and reduce it to a series. And so that may make it easier for us to find solutions when the cases that we're looking at are very, very messy. So what we're doing is we're taking some constant a, multiplying it by r, the common ratio, and each term has an exponent 1 higher than the previous one, because of course this one is implicitly ar to the 0, and this is ar to the 1. Now, here's a very interesting result, and we're not going to prove it here, but if the absolute value of r is less than 1, that means that the terms are, of course, getting smaller because we keep raising them to a higher power. And it turns out that in the limit, they add up to a over 1 minus r. So why don't we try an example and just see how that looks in Excel. So suppose, for example, a is 2. R is 0.8. It has to be less than 1 in absolute terms. So what that means then is that, let's say we have n is 1, 2, 3, etc. AR to the n. Well, actually, it starts. If I'm going to do it this way, it's n minus 1. That's why. Okay, great. Okay. So that means we're going to have 2b1 times b2, and the exponent will be n minus 1, e2 minus 1. So you can see the numbers are getting quite small. Now, what we're suggesting here is that the sum is converging to a over 1 minus r, which equals 2 over 1 minus 0.8. So it says here the sum should be converging to 10. Oops, sorry, that's this plus G2. Oh, yeah, I did it again. All right. So let's see. Does it look like they're getting close to 10? It kind of does, doesn't it? It sure does. So in the limit, as n goes to infinity, the sum of these terms is approaching 10. All right. Now here's one that we can try out. Although it may not be immediately obvious, this could be thought of as a geometric series, because if you write out the first few terms, you'll see the pattern. 4/9 plus 8/27 plus 1681. And if you want to be clever about it, you can rewrite this as, look at that. There is a pattern hiding in there. And you can see sometimes the challenge of these things is finding those patterns and seeing, hey, is this geometric or not? But here it clearly is, because R is 2/3, and luckily for us, it is less than 1, which means that this is a convergent geometric series. And so the sum of the terms in the limit will be 4/3. Wow. Okay, now we're going to see more of these interesting geometric series as we go along, when we're trying to take a function and convert it into a series. You'll see what I mean when we get to that point. The next interesting type of series that we want to look at is something called a telescoping series. What's happening here is that you've got like one minus another plus another plus minus another. In other words, the pattern is such that a very large percentage of the terms ultimately end up canceling each other out. So I guess telescoping, where you can collapse it. So you have a huge long telescope, you can collapse it to a little tiny thing that you can carry in your pocket. So here you'll see there's a lot of cancellation. You may ultimately end up canceling all but 1 or 2 of the terms. So here's n1 over n. Now we've seen this one before. This seems to be a very popular series. Now partial fractions. Oh, here we go. Partial fractions. Okay, let's just quickly review this. It says, yeah, it tells us, but let's just demonstrate it. So if you're going to use partial fractions, remember, this is what you've actually got. Okay, and then we need a common denominator. Then we can just set the numerators equal to each other. Oh, no, something. Well, that's strange. Hmm. Because these just cancel each other out. So it looks like the answers are supposed to be 1 and -1. Oh, I think I get it. Because basically what it's saying here is that 0 is A plus B. And I guess what that means is that you can choose any A and B that adds up to 0, including the 1 and -1. So in other words, it's not a unique solution. So we'll just go with 1 and -1. And so if that's the case, though, this is what the pattern looks like. So you have 1 for n is 1. One minus 1/2. This is because this is, of course, 1/1. And then we have 1/2 minus a third. Then we have 1/3 minus a fourth. But here's the thing. And, this will go on and on and on forever. These cancel out. So you've got this 1 sitting here. And then at some point, you'll have another term. So here's what they're telling us. Each individual term has the form 1/k minus 1/k plus 1, or algebraically, we can rewrite this as oh, I see what they're saying. Yes. In other words, the term that does not drop out would be the last term. So in other words, if we get up to n equals 8, then let's see, what do we have? 1, 2, 3, 4, 5. Let's say that this is 6. One 6 minus 1 7. There we go. So in other words, if I only go up to 6 terms, all that remains is this 1 and this -1 7. And so this is our 1, and this is k plus 1. All the rest drop out because it is a telescoping series. So in other words, we can write the general form for sk as 1 minus 1/k plus 1. And of course, as k goes to infinity, at least in this case, we'll have 1 minus 0, which is just 1. Wow. Ooh. So yes, now obviously not all telescoping series add up to 1, because obviously, let's say instead we had 10 up here, or 3, or whatever the case may be. Okay. So testing, there's 2 formal ways of testing for divergence and convergence. They're called the divergence and the integral tests. So, the time for Excel examples, I guess, is over. We need to formally prove this. So in order for a series to converge, it must clearly be true. That is, n goes to infinity, term an goes to 0. So And that's because now, by the way, what is this part all about? If let's say k is 1. No, let's try something else. Let's try, I don't know. Actually, we could probably do it like this. If you now subtract the lower expression from the upper, these all drop out except for the AK. So that means AK could be thought of as the difference between two consecutive partial sums. And so we'll take the limit of that AK as the limit of these two. And so these are both, whatever they are, if they're equal to each other, they will be equal to each other if the series is converging. So this will give us a 0. If not, they are diverging. In other words, by taking the limit of AK, if it gives us something other than 0, which is equivalent to saying that these are different from each other, then the series diverges. But if we have 0, meaning that these are equal to each other, that means they are convergent. Okay, in the limit, that is. This is all in the limit. All right, now, if the limit as n goes to infinity of an is some specific constant other than 0, or the limit doesn't exist in the first place, then this series diverges. Okay, and it's that simple. Remember, we're aiming for 0 here, as we saw here, because that implies that the partial sums are converging to each other. All right, how about this one? If you substitute infinity here, you'll just get infinity over infinity. So we're going to use L'Hopital's rule, our old friend L'Hopital, which tells us that we can now replace this ratio with the derivatives. And of course, f prime of n, if this is our f, and this is our g, f prime of n would simply be 1. G prime of n, oh, that's so simple. So we end up with the third. The problem is that that's not 0. It has to be 0. So what this is saying is that the limit, although it exists, okay, therefore, the series diverges. Okay. Now, there's two more tests. Now, there's an integral test coming up, but we also are going to introduce the so-called ratio and root tests. Again, the whole point of these is determine if our series is convergent or divergent. So since there's so many of these, it's pretty clear that what we're supposed to do is choose the one that's the most convenient for the case that we happen to be working with. In other words, it's not the case that one of these tests is absolutely and always the best. So that implies that there must be times when one of these is the best choice. Maybe sometimes the integral test works best. Sometimes maybe the ratio test works the best. And there are times when, on the other hand, when we were required to use one of these, well, we won't see that until chapter 6. Okay, in other words, chapter 6 is going to introduce another class of series, actually, I shouldn't say one class, several classes of series that are very useful in practice. And these are the ones that we'll be able to use to replicate a function. And so it's a very interesting topic. And so, but I think we've had a lot of good material tonight, so maybe we can save the integral test for next time. The integral test, the ratio test, and the root test. And once these are done, we can move on to chapter 6 and look at what are called power series. And that will be followed up by a discussion about some even more important series, which you'll see can be used to give us an approximation to a complex function. Sometimes all we need is an approximation. And so these special series we'll be looking at are designed to make that possible. But that's enough for now. I think there's a lot to look forward to. But I think for now, we'll let it go here. We'll stop and pick this up next time with the integral test. Okay, so I'll see you all next time.